Welcome to a video lecture of EE351 electronic circuits. In this video, we will start a new section which is on AC to DC converters. So these converters are also known as rectifiers. You all must have learned about rectifiers. So as the name suggests, this type of converter is going to convert the AC voltage into DC voltage. Now we can classify these rectifiers into two categories based on the number of phases in the input. As mainly as single phase and three phase. Then when it comes to the single phase or three phase, we can again classify into two categories. One is control rectifiers and the other one is uncontrollable rectifiers. So this the control uncontrollable rectifiers are mainly built using the diodes. They are based on diode because for a diode we cannot control the forward bias condition or the reverse bias condition. It will depend on the voltage applied to the diode. The second type, these control rectifiers are based on the other power electronic devices. So they are mainly based on thyristors actually. You consider the applications, the thyristor based control rectifiers dominate, but recently there is more applications where the IGBT or MOSFET based uh, control rectifiers as well. So we will start with the single phase rectifiers. We will look at the uncontrollable rectifiers first, and then we will move on to the three phase rectifiers. So of this one, first we will consider about half wave rectifiers. First we will consider the half wave rectifiers, then we will consider the full wave rectifiers. So in the half wave rectifier, initially we will consider the uh, load is a resistive load. Rectifier connected to a this is the arrangement. We have the AC supply, diode, and the load resistor. So I will take the current as ID and the voltage drop across the diode as VD, current flowing through the resistor as I out, and the voltage is V out. So that's how I'm going to consider. So, and I will take this the voltage Vs is equals to Vm sine omega t. So if omega t is less than 0, at that time the Vs is going to be negative. So if the voltage is negative in the supply, then this diode D is going to be reverse biased. Therefore, the current flowing through the diode is going to be 0. Then this is the first condition. Then in the second condition, I will take omega t is less than or equal to 5 and greater than 0. So that means in this condition, Vs is going to be a positive value. So in here, I will consider this omega t less than. So Vs is going to be positive. So if Vs is positive, then again we can say that diode is going to be forward biased. Then in the third case, where 5 to omega t minus within 2 5. So during this condition, actually Vs is going to be again negative. So which means that the diode is reverse bias. So I will be using RB for reverse biased and FB for forward bias there here onward. So now here the diode is reverse bias. So in the three conditions, that would be the case. So if we draw the equivalent circuit corresponding to these two conditions, actually now here in this condition we have the source and the switch diode is going to be in this manner, and this would be our equivalent circuit. Whereas in this condition, we have the switch is open and we have the diode connection. So that's the how the equivalent circuit would be for the two halves of the supply. So then we will consider the waveforms of this condition. So first I will draw Vs, phi to phi, and omega t. If we consider the V out, now V out is positive only when the input voltage is positive. So V out would be equals to V in this condition. So draw V out. So this is 5 to 5 omega t. Draw a line like for our easy reference. Then if we draw the current, so current should follow the voltage. It is going to be sinusoidal in this manner. Further, if we draw the this I out, then we can draw the VD. So VD is going to be 0 during the positive half cycle because the diode is conducting, and the negative half cycle the supply voltage would appear across the diode. So this would be the waveform for the half wave rectifier with resistive load. So for this one actually you can obtain value for V out average, so which would be equals to 1 over 2 phi 0 to 2 phi V out d omega t. So actually we can consider only the first half cycle. 2 phi 0 to phi, we have Vm sine omega t d omega t. So this is the average voltage. So we can solve this one and we can prove that it is equals to Vm over 5. So that would be the average voltage. Then since we know the average voltage, we can calculate the average current. So we have to divide by the load resistance Vm over 5R. Next we can calculate the V out RMS, so which would be equals to 1 over 2 phi 0 to 2 phi V out is squared d omega d and the square root of that. So again, that is going to affect only during the first half cycle. In the negative second half cycle, it is going to be 0. So what you have is 1 over 2 pi 0 to 2 pi Vm sin omega t squared d omega t, and the square root of. So this is, you can prove that this is equals to Vm over 2. So the RMS of the output voltage is Vm over 2. So this can be further extended, and you can calculate the RMS current, which is equals to Vm over 2R. So that's the variation of voltage behavior of the converter with resistive load. So once we know these voltages and currents, we can calculate the output DC power. VDC is equals to V out average into I out average, which is equals to Vm squared over 5 squared R. So that is the AC DC output power. So similarly, we can calculate the AC output power. VAC, so we can calculate it from V out RMS times I out RMS, which will be equals to Vm squared for R. So we can calculate the efficiency or the rectification ratio as P out PDC divided by PAC into 100% if you want. Otherwise, this is going to be equals to 4 over 5 square. So you can prove it considering these two powers. So next in the part B, we will consider the case where the load is a resistor in series with a voltage source. So this is Vs, then we have the diode D, resistor R, and the voltage source E. So again I will mark this as ID and VD. So this is going to be the V out and I out. So we will take Vs is equals to Vm sine omega t, and actually we will consider that E is less than Vm. So Em is less than uh, E value. So if it is greater than, if E is greater than V in, for any case this is not going to be forward bias, but with this condition you can see that the is going to be forward biased. So we will consider, we will draw the waveforms, and we will see what is going to happen. So first we will draw the V in. So this is V in, and we can plot E value. So this is E value, and this is V out. So what we can consider is that there is an intersection point corresponding to the V and Vm, V and E. So the V out plotting. So this is the V in. So in this case actually we can the current the diode is going to be forward biased only when the V is greater than E. Otherwise the current is not going to the diode is not going to be forward biased. So during this time the voltage is 0. Thereafter from here to here the waveform will be followed, and after that the voltage is going to, output voltage will become 0. So if we plot the so this is V out. If we plot the I out, current can only pass during the forward bias condition. So in the rest curve condition the current will be 0, and the volt current will, actually this is this can be something like this, because there would be a finite current because of the finite voltage. So this, we would have this kind of a curve for the current. So this is omega t, omega t. I will take this point as t1 and this point as t1, pi to 5. So the theta 1 and theta 2 can be found. In these conditions we can write V is Vm sine omega t, Vm sine omega t is equals to E. So from this one we can calculate the theta 1 is equals to sine inverse E over Vm. Then we can write theta 2 is going to be equals to 5 minus theta 1. So from this equation we can find out what would be the uh, the what would be the voltage, and we can write equation when the current is in between theta omega t theta 1 to theta 2. During that time we can write the output current is going to be equals to uh, Vm Vs minus E over R. Okay, so I have made a mistake in this diagram actually. So at this point Vs and Vm Vs and E are same, so the current is 0. So we will have the current will start from 0 and it will reach a peak, and then again at this point the current is going to become 0. So this is the output current. So you should be able to draw the diode voltage based on the uh, power values, based on the uh, voltage across the induct diode. So in this video lecture what we discussed was the single phase half wave rectifier. So we considered the case with the resistive load and resistive load plus a, voltage source. So with that we will conclude this video. Thank you.